Tesla's journey toward vehicle autonomy and leadership in artificial intelligence is built on a foundation largely invisible to most: its ambitious proprietary chip development program. It all began in 2016 when the company's engineers realized that off-the-shelf processors were limiting their progress toward autonomous driving. While competitors relied on ready-made solutions, Elon Musk and his team decided to take a bold path, designing their own silicon architecture, a risky bet that would forever transform the company's technological DNA. By recruiting elite talent, like Pete Bannon, a former architect of Apple's A5 chip, Tesla initiated a secretive project. For years they worked behind the scenes until 2018, when the first public announcement came. Hardware 3.0, an onboard computer that outperformed its NVIDIA predecessor by 21 times. The secret lay in two specialized neural processors designed exclusively to execute Tesla's computer vision algorithms with unprecedented efficiency. The strategic choice of less expensive LPDDR4 memory, offset by an innovative architecture, revealed a core principle: maximizing performance without incurring prohibitive costs. As Hardware 3.0 began equipping Model S and X vehicles, Tesla was already looking further ahead. Enter Dojo, a supercomputer conceived not to run neural networks but to train them on an industrial scale. At the heart of this colossal machine are D1 chips, true masterpieces of engineering with 50 billion transistors each. The brilliance of the design is evident in how 25 of these chips combine into tiles, creating processing units that defy thermal physics. Each tile dissipates 15 kilowatts of power, equivalent to 20 hairdryers running simultaneously in a space the size of a tablet. The bet on revolutionary packaging, using TSMC's InFO-SOW technology, allowed Tesla to stack performance while managing energy consumption. Each Dojo rack, composed of 6 tiles, delivers 54 petaflops, raw power sufficient to process years' worth of driving video in hours. But the real revolution was yet to come. In 2024, the company unveiled its system-on-wafer approach, where dozens of chips are printed directly onto a silicon wafer, eliminating communication bottlenecks and reducing power consumption by 30%. While investing billions in training infrastructure, Tesla did not neglect its vehicles. The modular architecture of its onboard computer allowed the company to rewrite software during the global chip crisis of 2021-2023 to use alternative components, keeping production active while competitors halted assembly lines. This agility stemmed from vertical integration. Controlling both hardware and software enabled rapid adjustments that saved the company from billion-dollar losses. The challenges, however, are proportional to the ambition. Protecting intellectual property became crucial, culminating in lawsuits against companies attempting to replicate Tesla's innovations. In 2023, a legal action against China's Bingling Intelligent Technology highlighted the strategic value of these developments. It wasn't just about chips, but an entire machine learning architecture optimized for vehicle perception. The next chapter of this saga is being written in Buffalo, New York, where a $500 million investment is building Cortex. This AI training supercluster, completed at the end of 2024, stores exabytes of video data captured by millions of Tesla vehicles on the road. By combining 90,000 NVIDIA H100 GPUs with 40,000 units of its own AI4 hardware, Tesla has created a hybrid ecosystem where algorithms evolve in continuous cycles. Every millisecond of real-world driving feeds virtual simulations that refine the system daily. Musk's vision extends beyond vehicles. Dojo and Cortex represent the foundation for Optimus, Tesla's humanoid robot, whose spatial processing and real-time decision-making requirements mirror those of autonomous driving. This synergy between platforms creates a multiplier effect. Advances in full self-driving, FSD, propel Optimus forward and vice versa as chip architecture evolves to serve both. Economically speaking, the strategy is beginning to bear fruit. While internal development requires massive investments, Tesla estimates that its proprietary chips deliver performance equivalent to commercial solutions at 1/5 the cost. By 2025, with its next-generation Dojo chips in production at TSMC, the company projects a 40% reduction in cost per million virtual miles trained, a critical metric for achieving Level 5 autonomy. For consumers, this silent revolution translates into software updates that transform older cars into smarter vehicles. 2019 Model 3 upgraded with Hardware 3.0 gains new autonomous capabilities years after leaving the factory, a living testament to the advantage of modular architecture. Meanwhile, Dojo's continuous learning allows Tesla's global fleet to collectively improve like a neural swarm, where each car contributes to the intelligence of the whole. Critics point out risks. The complexity of vertical development could scatter efforts, and betting on unproven technologies like system-on-wafer introduces uncertainties. Additionally, reliance on third-party factories like TSMC leaves vulnerabilities in supply chains. Tesla counters with numbers. In internal tests, its current hardware processes 100 frames per second from camera data compared to just 21 frames from its previous system, reducing critical reaction times during emergencies. The legacy of this program extends beyond the automotive industry. Innovations in chip packaging and high-density cooling are attracting interest from cloud computing companies and even space agencies. NASA, in partnership with SpaceX, is exploring applications for this technology in autonomous navigation systems for interplanetary missions, a testament that silicon developed for terrestrial roads may one day cross into outer space. Meanwhile, on Earth's roads, millions of Tesla vehicles collect data that fuels a virtuous cycle. Every successfully negotiated turn or avoided obstacle is processed by Dojo's D1 chips, refining algorithms that return to cars via over-the-air updates. This self-sustaining ecosystem, where hardware and software co-evolve, is redefining not just transportation, but also machine learning applied on a planetary scale. The future promises even greater leaps forward. Rumors about an experimental optical chip replacing electrons with photons for neuromorphic processing suggest Tesla is already exploring post-silicon technologies. Meanwhile, integration with Starlink enables real-time map updates and driving, data uploads to the cloud during traffic, connectivity that turns each vehicle into an active node within a global neural network. In this technological race, Tesla has charted a singular path. By rejecting off-the-shelf solutions and embracing the challenges of vertical development, it has created not just chips, but an entirely new paradigm of innovation, where cars are computers on wheels, factories are AI laboratories, and the dream of full autonomy inches closer one transistor at a time.